Alright, so here we are again. This time we have a transfer function that we need to do on a two tanks in series. So we have all this is, some of this is the usual, but we have new things here like jacks, which is a more powerful version of numpy, I guess. Or at least that's my understanding of it. And we have some other things from jacks here just to be able to make jacks work. So here we go. And we've got the size of our inlet holes and the size of our cross-sectional areas both being 2 here. So with that we can set up the initial steady state, time, height, and the inlet streams. That's what U stands for. So H1 and H2 are going to be equal to H, and U1, U2, and U3 are all going to be equal to U, and these are going to be what we set up for different things after. So then we've got H1 is equal to AH times H1 to the half power and then H2 is going to be the same thing, but with H2 my bad, these aren't supposed to be heights, these are supposed to be inlets, the Q, or rather the tank outlets. I don't really have a picture of the tank right now, but the tanks in series should be, there's one tank feeding into another, there's 2 streams in the first tank and 1 stream in the second. So that'll be important, and I'll show you what that is in a second. So we've got Q2 is equal to AH, and it's times H2 to the half power. So then we want to return the array to get ready for linearizing it, because these are not linear functions. So then we've got, I believe it's U1 plus U2 minus Q1 over AC, and then U3 plus Q1 minus Q2. I don't know why I wanted to capitalize these, but that's not right. And that's also divided by the cross-sectional area. So then we get that. Alright, so then I think the next part is solving that initial steady state. So Hn is equal to root with an anonymous function. With respect to the variable x, and then it's tank with respect to h, it's 0x. I'm realizing I forgot a piece of that when I pushed u in, so we need u in is equal to an array, but specifically a jacks array of I think it's 2.5. No, there's 2 and 0.5. Okay, 2.5 and 0.4. So 2.5 and 0.4. That's U1, 2, and 3. Alright, so now we can... Oh, duh. I should probably properly format these. I bet this is also gotta be just in case. Alright, now I can go back. And then we want an array of, or just rather 1 and 1, and that'll be the initial. Oh, I did it wrong. You're supposed to not be capital. You're supposed to not be a squiggly bracket. Alright, and then this needs to be .x because we only want to write that value. Oh boy. Alright. I figured out what I was doing wrong. I just didn't remember to put array here. So now it works, and now we have the steady state heights of both tanks, at least initially. So now we're ready to start doing the Jacobians, if you will. So we've got JH, and these are gonna, or we've got rather, and we're gonna start on the Jacobians. So we've got FJH, the function of the first Jacobian, which is equal to, I believe, Jax dot Jacobian. And we want that to be tank and 1, and then we want JH is equal to the function of the Jacobian. It's 0 H in and U in, and then we want to print JH. Alright, there we go. And now we go to JU to get the other half of this, because these are all the heights and whatnot. And then we would, this is gonna be, the other one's gonna be the you'll see, it's gonna be, I think, we'll see, I guess. Jacobian with the same thing, tank and 2, and JU is going to be equal to FJU, and 0 H in and U in again, and then we want to print JU. Alright, so now these are the linearized models. And now we want to make the state space model, so the system is going to be equal to state sig state space, and we need JH and JU, and then we need the array of our initial heights, and then another array of filled with zeros, and then we print, and I believe that's right, state space model. Should just put all those together. Linear time invariant setup C and D matrices to isolate H2. I think that's what we've done. Stack R. Yeah, that's isolating h2 by having h1 as 0. So we have the h2 isolated now. So now we need to do the transfer function. So we have and denominator first. Set those equal to signal SSF SS2TF. So that's the second state. Steady, it's this something transfer function. I think it's steady state transfer function. So actually I'm going to, because these are the exact same things inside here, just do that, save myself. Oop. That would be why. Okay. Except we also have an input equal to 2. And then we want to print the numerator and denominator. Okay, I get that so far. And then we want to actually create the transfer function. So H2 U3 H2U3 transfer function is equal to signal dot transfer function with respect to numerator and denominator. Oh. Alright, that's good. Alright, now we gotta plot everything, because we've got almost every... Actually, wait, I'm wrong. We do have to compare this to solve IVP, so then we need the result is equal to solve IVP. Respect to time and height. So then UN plus for A 0 and 0.1. Once we're done with that, we need is the initial. Wait, we need 0 to 20 is the time span. We need 20 minutes. Then we need the y0 is hn. And then the usual method is equal to redo. And then dense output is true. All right. Oh. Oh, that's even worse now. This isn't supposed to be 0 and 0.1. It's supposed to be 0 and then 1. That's why it's wrong. Okay. So now we're actually ready to compare both of these two things. So we need a time and the deviation of height, and set that equal to this right here, h2u3 transfer function, and then we want that to be a step function. Then we want a time plot. That's equal to linspace. I want you from 0, and we want you from 0 to 20 with 100 intervals. And then we want to make subplots. X is equal to t, y is equal to h2 deviation, name is equal to linear, because this is the linearized model with the Jacobian and stuff, and then time plot. Okay, nonlinear. Let's see if I did this right. Not quite. Close, but not quite. This looks a little funky. Alright, so I was also supposed to add the initial steady state to the linear one, and it's looking okay, but still wrong. Okay, so I think I missed one more line of code, and that is I do have to define h1 and h2 and make them equal to the result of that with respect to the time plot. The result of solve FAP first. And we'll see. I don't know why you're still wrong. I think I see what I did, and this is supposed to be h2 because I already set h2 to be in line with that initial steady state. There we go. Now that's correct. And this the nonlinearly solved one is in fact much more accurate than the linearly solved one. However, this linearly solved one is more versatile for actual computer programmers to, I don't know what they would need to do with this that you couldn't, but it's supposed to be better for computer programmers to use the linearized versions. Alright, and that's it until the next part of this homework.